Hello you guys, how you doing today? And today we're gonna derive Young's modulus equation. Young's modulus. I am so sorry for my bad pronunciation. But before we go tackle and see how we derive Young's modulus equation, we need to know what Young's modulus equation means. And Young's modulus is the ratio of stress to stretch for a particular material, and it does not depend on the size or shape of the object. Right here, I have Young's modulus equation already derived, and is F divided by A divided by delta L divided by L. And this is, F is the force, A is the area, delta L is the stretch, and L is the length. Now let's go hit and derive this problem. So let's imagine this. This right here, this line right here is a spring. Yes, this is a spring. And Young's modulus is trying to go inside this spring and find the spring constant of this spring by atom-wise, like very, very small. So this will look something like this. And here, all this empty space, all this white space you're seeing right here on the sides, on the top, and everywhere, there's atoms. Atoms everywhere. It's just atoms everywhere. And it will look something like this. We have my atoms in series and my atoms in parallel. And in this spring, I'm going to put a weight. This way right here. And right now, I don't really care what mass this weight has right now. So when I put this weight, my spring will stretch this size, this much, and that will be my stretch. And I know that the original size of my spring is L. I have D, that's the diameter, the size of my atoms, and my area, A. And I know that the force of the spring is equals the spring constant multiplied by the stretch. And I can solve for K for my spring constant. That will be K equals mg, mg is force, divided by the stretch, S. And I need this is for big. This is big for like spring. Like I use like the spring outside. I want the atoms. So to find the atoms, I need to find the equation for the series and the equation for the parallels. So series is, this is series right here. Series is NS equals L divided by D. My L divided by the D, the diameter of every atom. And my parallels right here, my parallels is NP, P for parallel, is the area divided by D, D squared. So because my series, if I have something in series, will have a lower spring constant, I'm gonna put the series on the bottom. So we'll have NP multiply Ks divided by NS. And this is equals to A times Ks divided by D squared multiplied by L divided by D. And this is equal to this. They're the same. There should be no confusion. This and this. No confusion. So I can cancel one D. This D will cancel with this, and we'll have just this left. I have 8 times Ks divided by D times L. Sorry. And I know that this and this are equal to each other. I just proved that this and this are equal to each other. So I can solve for my Ks, and my Ks will be equals mg force times the stretch times dl times LA. See, this is equal to this, so I get this. And by fractions, I can solve this as mg divided by A divided by stretch times L divided by L, sorry. So from all this work, I derived the Young's modulus equation right here. And with this, I can, this is Young's modulus equation right here. Right there, from the very beginning. Thank you.